All right, looks like we are working. This is going to be the latter end of chapter 3 now, and after this we'll get into chapter 4. Again, we're looking at no nonsense quantum field theory. This is kind of a big textbook, but we've made a good chunk into it. I'd say chapter 3 ends, actually maybe I take that back. Chapter 3, I want to see how much of a dent we've made into this book, actually. I'm kind of curious. Okay, chapter 3 does talk about, so we've done about that much of that much, right? So we're at this point. Okay, we're going to be talking about gauge fields, or local coordinate fields is what the book calls it. And so let's get right into this. So gauge fields. So without really going into too much history or anything like that on gauge fields, I want to teach it in sort of kind of a similar way that the book teaches it, but also in a way that I think might be a little bit easier, because I found that the book was just a little bit beat around the bush a little bit, I think, in teaching what exactly these gauge fields were. And what I'm going to do is I'm going to jump straight to the punchline first, right? Because oftentimes students get bogged down in the weeds and they want to know what the point is of these chapters. The point, there's going to be 2 points made in this video. One point is a covariant derivative. So we're going to talk about this thing called a covariant derivative, which looks like this. Sorry about my dogs making noise in the background. So this is this is a covariant derivative. The covariant derivative, what it does is it takes into account the change in, say, your scalar, if you're looking at a scalar field, as you move from one point to the next. So the difference between the scalar here and the scalar here, while also taking into account a change in like a coordinate system. Okay, I like to think of these as coordinate systems. This object right here, right? Even though it's a vector, I like to think of it as something like a coordinate system because that's what makes sense to me. And I'll explain why. And then we have, we're going to get to a point here where we have a scalar field or any sort of field, right? We have some scalar field. It's located at x mu. And if we wanted to transform that, right? So my dog is whining a little bit. I apologize for that. So say this is a transformed scalar field at one point. Well, that's equal to the original scalar field at the same point, plus some extra factor here that's going to be located at the same point. And this factor here we're going to derive. We're going to see what it actually is, and we're going to see why it's important. So let's get right into this. I'm going to erase the punchlines, and we're going to talk now about our field. So here's our field. And our field, again, this is a 2-dimensional field. It could be a 3, it could be a 4, 5-dimensional field, if you will. We can expand this to multiple dimensions. And what we want to do is we want to start off at a point here. So we're starting off at a point here, we'll call it A. And we just want to see, we're really just interested in what happens if we were to travel from point A this way in the x direction. So say this is a small distance in the x direction. Similarly, we can do the same thing with a small distance in the y direction. Okay. I have a fly flying around here too. It's kind of annoying. So what would this look like? Well, here we would have our field at A, our field value at A. So A is the label of the point. Phi of A is the field value located at that, as a field value at that point. Excuse me. If we were to move dx away, we would get we would get a difference between the two. So A plus dx. Okay. Now we can imagine, okay, if the point at A, the value at point A is the same as the value at the point as we go in the dx direction, that's the next point. If they're the same, then the difference should be 0. Right? But here's the thing: what if they're the same, but the difference is not 0? Think about that for a second. You could pause the video. That might mean that there could potentially be some sort of change in a coordinate system as we go from, sorry, my dogs are being weird, as we go from point A to its neighboring point. So we could subtract off this extra term here. I tend to want to call this A, but I'll call it C. This is some extra term that accounts for any potential change in a coordinate system. And we'll say that this is at A, this is located at point A, as we travel, if we were to travel in the X direction. If we were to travel in the Y direction, this would be a Y, and so forth. So we can generalize this. We can generalize this a little bit. We could say phi at x mu minus phi at x mu plus dx minus c at x mu going in the x direction. All right, so I'm just labeling things a little bit differently. But now what we can do is we could say, well, suppose dx, I'm just going to change dx here with a little unit vector. All right, so if I change that with a little unit vector, I get x mu minus phi of x mu plus e I. This is really just changing in notation, but this is stuff you might see in other books also. Minus c x mu at I could say I, the ith component of c. All right, so nothing's changing. I'm generalizing more and more. But what we're able to see here now is that this, if we were to divide everything out, by that small unit vector that we change, so you can then ask the question, what happens as that unit vector gets smaller and smaller and smaller if we were to do this division? Well, we're getting to something that looks like a derivative right here. So this would be the partial derivative. This would be the partial derivative as you go along the EI direction, okay, of phi, right? So of phi. And this extra term here would be C. Again, it's located at x mu, right? This is located at x mu. And you're going in the EI direction. We can generalize this just a little bit more. We want to be able to generalize because then we want to test these generalizations to see if they're true or not. The human mind is really good at making these types of generalizations. So again, this right here, we could take the limit, right? We took the limit here as e to the I approaches 0, and we got a normal partial derivative as we travel in some direction, we can really kind of just shrink that down to d mu, right? Because what d mu stands for is d dx mu, right? And so mu runs from 0 to 4, or 0 to 3. And so as that that would be the derivative as you go in each orthogonal direction within your manifold, or within your space, right? And in this case of special relativity, as we said, we're dealing with 4 dimensions, right? X, Y, Z, and time. Right, so again, mu goes from 0, which is associated with the time derivative, and then 1, 2, and 3, which is associated with the 3 spatial derivatives. And then we have this minus c part, and this is going to end up being also, we're going in the EI direction. That's just contracts down to mu, but this is also located at x mu. So this is our covariant derivative, right? So we could take the covariant derivative, for example, would be the 0th component of the covariant derivative would be something that, say, looks like this, located at x mu. And I could put a 0 there. But this point really here, this means that this is actually a field, right? This, by virtue of putting this x mu right here, we're saying that this object is a field in and of itself, and that is what we're calling a gauge field, right? Because there's a value for this at every point in space and time. So here's the kicker. When we do this, when we say that we want to compare 2 points that are next to each other, we need to be able to have a notion of something of like a coordinate system, so that we can, at each point, so that we can compare the two. Okay? So once we do that, then we're able to compare the two, right? You need a coordinate system to be able to compare the two values, okay? And what we're doing here when we take the covariant derivatives is we're accounting for any potential changes in that coordinate system as we go along each direction. So we have this sort of like a coordinate system, if you will, at each point in space and time. And that's what the gauge field is. In the book, they call it something of like a glue field, right? This is what glues everything together. It's what enables you to compare points with one another on the field, okay? This is extremely important, and this is going to be extremely important when we talk about bosons. Again, so I'll circle this right here. So this is our covariant derivative, and this here is our gauge field. Right, so the covariant derivative, again, takes into account the spatial derivatives along with any changes in our coordinate systems. And this is a very, very important derivative, and we'll get back to this later. This is sort of a primer on, or at least getting our feet wet with this idea of a covariant derivative. We're gonna not really shift, but now we want to take into consideration what might happen if we're at a point, and we're at point A. We're at point A, and we want to know now. This is going to be interesting. We want to know what happens if we were to go this direction, then this direction, and then this direction. Because what we've said earlier is that we can compare the point A with, say, the point B, and the point, I'll make these each one different colors. I'll make this one purple. point C, and I'll make the next one yellow. And point D. Oh, I really like that yellow. So when we move from point A to point B, we want to account. So we're going to start here. We're going to start off by considering our value at point A. Okay, and now we move from point A to point B, and when we do that, we want to take into consideration the change in our field, or the change in our coordinate system, as we go in the x direction. Right, so this is going to be, and I want to add this. We'll see why. I'm going to consider going this way and going up being plus, and I'm going to consider this way and this way as being negatives, just for convention. So this, we're going to call this A. We're going to be adding a change in our coordinate system, or the value of our coordinate system at as we go from the change in the x component of our coordinate system as we go from as we go from point A towards B, right? So so this is at point A, so maybe I'll use C's like I originally done. So as we go from point A plus, actually, I'm going to do it like this actually, because it might be a little bit easier to picture. So when we go with this direction from A to B, we're adding our, we want to add some potential change in our coordinate system, right? And that change in our coordinate system is going to be something that looks like this CX. So this is a change in our x component, and I should put A here actually. So this is a change in our x component at A. And then here we want to add the change in our y component, because we're going up from n, or I keep on wanting to put n for some reason, A, plus EX. So again, this is from our shifted direction, because we've gone A plus EX, and we're going up, right? So we start at A, we went this way, right? And then we go from here, and we go up. This is a change in our Y, right? So it's like we could sort of read this as going from this point to here, okay? Now then we're gonna go in the opposite direction. Keep on wanting to put A for some reason. C, and this is going to be A plus EY, right? Because now we are in an upward position from A, but this is a change in our x component because we're moving left. So this is going to be a change in our x component. And then we want to when we're coming back down to A, from D to A, this is a change in our component again, as we go from A, we're changing in Y, right? So this is, the reason I put A here, not D, is because, again, we're traveling downward, so we're traveling in the Y direction. So there's going to be a change in our Y. You could see here, here and here, right? We're moving in our x directions. Here and here, we're moving in our y directions. And so essentially what we're doing is we're considering the changes in each direction of this coordinate system. And the reason that this is a y is because, well, it could be d, right? It could be d, but it's minus, right? So this is really just a change in the sign here. So it's like flipping the arrow, right? So now what we can do is we could put this all together. When we put this all together, we're gonna start at our original value at a, and we're gonna basically add all this up. These are changes in coordinate systems, and we're making a closed loop. We're making a closed loop in this field, in this scalar field. So CAX, and then plus CA. Actually, what I want to do, I'm going to skip a step, but I'm going to skip a step doing it in a smart way. What I want to do is that essentially I want to add these up, right? I want to add all of these up to our original value because we want to be able to see what happens, what might happen here. We want to, because we have our original value again, plus any possible change in our coordinate system. And so, and all of these factors are what account for the possible changes in our coordinate system. So what I want to do actually is I'm going to choose a different color really quick. And I want to add this up with this. I just want to group them together, and I want to group this with this. Because these are this here is motion y, this is motion in y. This is, or changes in y, changes in y, this is changes in x, changes in x. So I'm going to do that. So what this ends up being is a minus sign, black. This ends up being a minus sign CA plus EY x plus CAX. Right. Oh, whoops. And then we want, actually I'll get rid of the brackets really quick. And then we're gonna have plus CA plus EX y minus CA y, like that. Now we want to look at, if we look at these, this here is going to be essentially a partial derivative in the x direction, right? Because again, we're traveling in the x direction here and here. So this is a partial derivative in x of our c y, right? Because we went from, even though we're moving in x again, even though we're moving in x, we started at a y point, right? The shifted point in the y direction, right? And then this part here, well, that's just going to be the opposite, dy cx. Okay. And then if we want to keep things a little bit more consistent in terms of our signs, this ends up being, let's see here, if I can get the signage right, we can get, if I make this a minus, I'm not going to do that actually. We have, I'll undo that really quick. Okay, so what we have is, again, group these together in parentheses. Group this in parentheses like that. And so what we end up getting is, I want to see here really quick. If I made this plus, I could make this a minus. I just want to make things a little bit easier to see here. And if I made this one a minus, this is really just changing signs, but when you change signs again, you have to take into account all of the changes in the signs, which is a little bit tricky, but when I do that, then that means that did I miss something here? So we went, oh, that should be minus, that should be plus. I think I messed up a minus sign here. The point is though that the signage doesn't really matter. So if I make, if I take a minus sign out of there, that's going to be, it's going to look like, okay, I think, okay, I'm just confusing us too much here. I'm gonna get back to making this a positive. Okay. And if I made that a negative, that would really just flip the sign. Yeah, I'm not going to do that. So we have our original point plus all this stuff right here. And what is this stuff? Well, this is defined as x, y, and since C is located at some point, like we said earlier, well, this is located at some point also. And we can, instead of being in a flat space, we can have this be in multiple dimensions. And what we end up getting is something that looks like this. So the field at, the field value is at some location. And we're adding this object here to take into account our changes in our coordinate system as we go along the closed loop. We can do that in multiple dimensions. Right? We can consider closed loops in multiple dimensions. And that's what this object is. And this all hinges on the fact that we relied on these glue fields, right? These objects right here, right? These C's, these coordinate system changes. And so that's what this is. This thing takes into account all the coordinate system changes as you go from one point and come back to that point within your manifold. And the thing is that this doesn't necessarily end up being zero, right? Because you might think this is equal to it should be equal to x mu, right? So, but if it was equal to x mu, you could take this, subtract it from both sides, and you get that this is zero. But what's interesting is that it doesn't necessarily actually have to be zero. Right? Your perspective at one point, for example, as you travel along the closed loop could be different once you get back to the loop. It's a little bit weird to think about. But again, this is going to be related to our electromagnetic field tensor, and that's what this thing is actually called. But this fundamentally relies on changes in coordinate systems as we travel from one point to the next. And this is also, the book alludes to curvature, right? So when you travel on a sphere and you keep your arrow perpendicular, whatever, to the closed loop as you go along this as you go along the sphere, you end up seeing that the end vector is not the same as the starting vector. And so there is some relationship to curvature here. I'm not gonna bother talking about curvature. The book briefly mentions it, but that's something I think for general relativity, that more so than it is for quantum field theory. Even though there is an attempt on the part of physicists to merge ideas in quantum mechanics and ideas in quantum field theory with curvature. And this is a very interesting area of study because it's something that it's something that scientists are trying. It's a means by which we try to merge general relativity, which is the physics of the really big and the physics of the universe, black holes and all that kind of stuff, with the physics of the real small. Right. So if we can somehow understand curvature in both domains, we might be able to have a unified theory. And so we can consider curvature in quantum field theory, and we will do that. But that's something that this book doesn't really go into that much, and I intend to keep it that way for this book because, again, these playlists are on a book by book basis, or PDF by PDF basis, or anything like that. But that's what this is going to be. That's what this is going to be like for this playlist, right? So that's it for this video. We've talked about, again, this object that's going to take into account shifts in our coordinate system as we traverse a closed loop in our system, or in our field, and our covariant derivative, right? This right here. So the covariant derivative, again, is the derivative, or it takes into account the difference between two values on a field and any potential changes in our coordinate system as we travel along that field. And that's, again, what these C's are. Again, my apologies for being stuck up about the signage here, but if that's something that actually kind of bugs you, and the notation's different everywhere. I believe this actually is a minus, right? So if this was a minus, you can just play around with, or this is a minus sign conventionally speaking, but you can play around with that to see what would have to happen is that if this became a minus sign, then that means this would have to become positive. This here is just inverted, basically, but it's still a difference in our y direction, right? But yeah. So with that being said, I'm going on a little bit above 30 minutes, and so I'll see you guys in the next one. See ya.